Hi everyone! In this tutorial we will learn about how you can convert triglycerides like vegetable oils to biodiesel through transesterification. First, we're just going to review nucleophiles and electrophiles because we need to understand how they work in order to actually understand the transesterification process. So nucleophiles are molecules that donate electrons in reactions, and they have high electron density. In Latin, their name translates to love the nucleus. Electrophiles are molecules that accept electrons in reactions, and they have a lower electron density. In Latin, their name translates to loves electrons, which makes sense because they are accepting electrons. In nucleophilic addition reactions, a nucleophile adds to an electron having a double or triple bond. The electrons in the electrophile adjust to accommodate the new bond to the nucleophile, and they can add to carbonyl groups or to alkenes. Addition reactions are often followed by simple acid-base reactions. Nucleophilic substitution reactions is when a nucleophile reacts with an electrophile to replace another group, and this is called the leaving group. So with carbonyl compounds, this occurs through an addition-elimination mechanism of carboxylic acid derivatives. So first, the nucleophile adds to the carbonyl electrophile, but this compound has what is called a leaving group, so the CO double bond can reform and expel that leaving group. These reactions are often preceded as well by acid-base reactions. Here's an example of nucleophilic addition. So blue is for our nucleophile and red represents our electrophile. So the addition of the nucleophile pushes the electrophile onto the oxygen, making it a negatively charged compound. And this creates our new carbonyl compound. Here is our representation for a nucleophilic substitution mechanism. So the first step is the exact same as before. It's the nucleophilic addition to the carbonyl compound, which creates a new bond. And we can actually go further from here. So the leaving group has been replaced by the nucleophile, and this is why we call it a substitution reaction. So what is transesterification? It is the process of exchanging the organic group R2 of an ester and the organic group R1 of an alcohol. The carbonyl carbon of the starting ester reacts to give a tetrahedral intermediate. So this either reverts into the starting material or it proceeds to the transesterified product. It's an equilibrium reaction, therefore it's reversible. And this process can be used to convert vegetable oil into biodiesel fuel, which we are going to be learning about today. First, we are going to discuss the characteristics of vegetable oil. So it's a triglyceride obtained from plants and it's found in seeds, nuts, and fruit. We all know that vegetable oil is used for cooking, so it's important for ingredients in food. Molecules of vegetable oil consist of a glycerol and fatty acids. The three long chains of carbon atoms are attached to a glycerol molecule to make one molecule of vegetable oil. You can see that in the picture here. They have a higher boiling point than water, and they also separate in water because of the different densities. They are very thick due to their high viscosity, and this also makes them able to be solid or liquid at room temperature, depending on the viscosity. Now, in order to reduce this high viscosity, we have to separate the glycerol molecules from the three fatty acids, which is actually the transesterification process. Now, this is the chemical reaction used when converting vegetable oils into biodiesels. So it requires 1 mole of a triglyceride, and our triglyceride is vegetable oil, and 3 moles of an alcohol, which we usually use either ethanol or methanol. Methanol is more favorable over ethanol because it requires less water during the process, and ethanol you have to separate the water and it's a much longer process. We also need a catalyst to speed up the process, so we could either use an acid-driven catalyst or a base-driven. Using the base as a catalyst is the fastest process and it requires the lowest amount of temperature and pressure levels, but acids can also be used. We would use an acid as a catalyst, for example, sulfuric acid, when our vegetable oil has a really high acid content. It involves the reaction of fatty acids with alcohol, where the acid catalyzes the reaction by donating a proton to the carbonyl group, making it a more potent electrophile. It requires temperatures above 100 degrees Celsius and over 3 hours to complete the reaction. And in the end of the production, glycerol is difficult to obtain, and there's a risk of corrosion in the process as well. So overall, it's a less effective method. Whereas bases, on the other hand, either sodium hydroxide or potassium hydroxide, they can be used to catalyze the reaction between lipids, which we know are fats and oils, with an alcohol. It catalyzes the reaction by removing a proton from the alcohol, making it more nucleophilic. It is more effective since it's the fastest process, and it also requires low temperatures and pressures. We are going to be looking at a representation of a base catalyzed reaction because it is more favorable and more often used than an acid catalyzed reaction. So our R1 value here is our alcohol, which is usually methanol or ethanol. Our R2 value is our triglyceride, which in our representation is vegetable oil. And B is just our base catalyst, which is usually something like potassium hydroxide. The first step is the reaction of the base with the alcohol, which produces an alkoxide and a protonated catalyst. In step 2, an addition reaction is taking place. So the alkoxide acts as the nucleophile and attacks the carbon, forming a bond between oxygen and carbon, placing the pi bond onto the double bonded oxygen. This generates, as you can see here, a tetrahedral intermediate ion with a negative charge on that top oxygen. Step 3 is an elimination reaction, and a pi bond is being reformed between the oxygen and the carbon. The leaving group is the original alkoxide group. So this forms our ester compound. As you can see, our original R2 group that was attached to the oxygen in our step 2 has now been replaced, and it is just the R group attached to the oxygen on our ester compound. And in step 4, the active species is regenerated and is reacting with the second molecule of alcohol that was produced in our first step. So this produces our mixture of alkyl esters and glycerol, which is just fancy for saying our biodiesel. Looking at the products of our reaction, so obviously we have produced a biodiesel, which is non-toxic and biodegradable, and its physical properties actually resemble petroleum diesel fuel, but it is the more sustainable option. If we look here in our image, we have produced a long chain between fatty acids alkyl esters. After the reaction, the biodiesel needs to be further purified by washing and evaporation to remove the methanol. There are also some byproducts produced in the reaction, which include soap, so that's through the process of saponification, some glycerol, excess alcohol, and trace amounts of water. Now, all of these byproducts need to be removed in order to attain the biodiesel. So to wrap up the presentation, I'm just going to go over a more simpler explanation of the process to get our biodiesel instead of like a more chemistry-based. So we did learn that a catalyst is needed to make our biodiesel, but before we even use this, our catalyst, which is a base, usually potassium hydroxide or sodium hydroxide, is dissolved into methanol and it creates methoxide. Then with our vegetable oil, we need to heat it and it's mixed with the methoxide to begin the chemical reaction. Once they're mixed together, the transesterification naturally occurs and we create our biodiesel. But when the biodiesel is actually created, it's hard to attain it from the product. In this picture, we can actually see the difference between using used vegetable oil and new vegetable oil. So old vegetable oil contains free fatty acids, which are a combination of diglycerides and monoglycerides. So if there are enough free fatty acids in the oil, we end up with lots of soap and not enough of a catalyst left over to break all the bonds of the remaining tri, di, and monoglyceride molecules. So in other words, we end up with soap, unconverted oils, and some biodiesel, so basically just partially reacted biodiesel. So to contour this problem, oil titration is used on the vegetable oil before using it in our reaction so that we don't create this soapy layer. Another obstacle in the process is when there's water present in our oil. This is because when oil, water, and a catalyst react, it creates soap. It doesn't create a biodiesel. So if your oil is wet, not only are you dealing with the free fatty acids eating up the catalyst, but the water is also going to use some of it to make soap out of not only the free fatty acids, but it's going to pull from the good fatty acids as well. So therefore, you should remove any water from the oil before you start the actual reaction. So that is my conclusion, and that's how you create a biodiesel from vegetable oil. Hope you all enjoyed this tutorial.